These men are in the process of increasing their plant's efficiency, and at the same time, they're making this area a better place to work. This is thermal insulation. It's used on many of the systems in the plant. Basically, thermal insulation is anything that blocks the flow of heat. High temperature insulation prevents burns and keeps work areas from getting too hot. On cold piping, sweating and freezing is prevented by low temperature insulation. And just like in your home, insulation in the plant saves money by making heating and cooling more efficient. Today we're going to be talking about how thermal insulation is used in industry. This means that we're primarily concerned with large-scale systems and the piping associated with these systems. Now, part of your job as a maintenance mechanic is the upkeep of insulation systems in the plant. We'll be talking about installation and maintenance of the four most common kinds of insulation: calcium silicate, fiberglass, cellular rubber, and reflective insulation. But before we begin our discussion of the different types of insulation, let's look more closely at the job thermal insulation is supposed to do. Thermal insulation is intended to do one thing: prevent the movement of heat. Now, in some cases, we're trying to keep things hot. We don't want heat to escape. Other times, we want to keep things cold. We're trying to keep heat from getting in. To see how thermal insulation does this job, we'll have to take a look at how heat is transferred between objects. Now, there are three ways heat can be transferred. There's radiation, conduction, and convection. Let's take these one at a time. Radiation is the first kind of heat transfer. The fiery furnace of the sun burns at a temperature of millions of degrees. This heat energy is beamed out in all directions, or radiated. When the radiation is intercepted by a solid body, like the Earth, that body heats up. Now, here's an example of radiant heat that's a little more down to earth. When a piece of bread is toasted by the heat energy of the glowing coils in your toaster, that's radiation. Conduction is the second kind of heat transfer. Conduction is how heat is transferred through solid objects. When one portion of a solid object is heated, that area contains more energy than other colder parts of the material. To even out the distribution of heat, energy is transferred to the relatively colder areas. If the object continues to be heated, a constant flow of heat takes place from the hotter to the colder parts of the material. Convection is the third and last type of heat transfer we'll discuss. Convection refers to the movement of heat through a fluid, like air or water. When air travels over a hot object, it picks up the heat and carries it along. A constant flow of air cools the heat source as it distributes heat to other areas. In a closed space, the natural convection flow of heat causes a circular air current as the hotter air rises. These three kinds of heat flow, radiation, conduction, and convection, describe the ways that heat can be transferred between objects. Radiation is how heat is transferred across empty space. Conduction is how heat is transferred through solid objects. And convection is the circulatory motion of heat in liquids and gases. Thermal insulation is designed to prevent radiation, conduction, and convection of heat. There are two ways to do this. First, radiant heat losses can be prevented by reflecting heat waves back to their source. The kind of insulation that does this is called reflective insulation. Second, conduction and convection can be prevented by surrounding the heat source with a material that doesn't conduct heat and seals off the source from air currents that cause convective losses. Materials that do this are called mass-type insulation. These two types of insulation, reflective and mass-type, are our tools for controlling and limiting heat flows. Reflective insulation consists of a shiny surface that reflects heat like a mirror reflects light. Sometimes thin metal foils are used. In other applications, layers of reflective metal work together to provide a greater insulating capability. Or reflective insulation can be used along with mass type for the maximum protection from heat losses. Mass type insulation prevents two kinds of heat transfer: conductive and convective. First, the material must be a poor conductor of heat. Different types of materials vary according to how well they conduct heat. Metals are relatively good conductors, as you know if you've ever tried to grab a hot skillet. On the other hand, wood and fibrous materials conduct heat poorly. That's because they contain dead air, air that's trapped within the material in small pockets. Air is a good insulator, but only if convective heat losses can be avoided. Dead air prevents convective losses because air that's trapped within the material cannot circulate and give off heat to the surrounding area. Mass-type insulation combines these two elements into one: a material that's a relatively poor conductor of heat and dead air trapped in pockets within the material. The effectiveness of mass-type insulation depends largely on the amount of air trapped in the material. If the insulation is compressed, some of the air is forced out, reducing its insulation value. The same thing happens if the insulation gets wet. The effectiveness of mass-type insulation depends on the amount of air trapped in the material. In a few minutes, we'll see how insulation is used on the job. We'll be talking about reflective insulation and three kinds of mass-type insulation that are commonly used on piping systems. But before we go on, let's take a minute to review what we've learned so far. First, we learned that insulation is a material that blocks the flow of heat. Second, we learned three important reasons for insulating: to protect workers from burns and high temperatures in work areas, to keep water vapor from condensing and freezing on cold piping, and to save money by making heating and cooling systems more efficient. To learn how thermal insulation works, we discussed the three ways that heat is transferred: radiation, conduction, and convection. We saw examples of two kinds of thermal insulation: reflective and mass type. Take a break for a few minutes and study the material in segment 1 of your text. Work the exercises, and be sure to ask your instructor any questions you have before going on to the next part. Well, you've learned some of the basics about thermal insulation now. You know what it does, and you know how it works. In the next few segments, we're going to be looking at how insulation relates to your job as a maintenance mechanic. We're going to discuss 4 of the most common kinds of thermal insulation and see how they're installed, removed, and repaired. The first kind of insulation we're going to talk about is calcium silicate. Calcium silicate is molded mass-type insulation. It combines lightweight with considerable strength. You'll see it used most often on high-temperature piping, like steam lines, because calcium silicate is high-temperature insulation. It can withstand temperatures of up to 1,000 degrees Fahrenheit or 540 degrees Celsius without burning or melting. Most plants have literally miles of this kind of insulation on its piping systems, so chances are you'll be working with it fairly often. Whenever you do, be sure to wear a filter mask and goggles to protect your lungs and eyes from dust, and gloves to keep the insulation from touching your skin. You see, many older installations of calcium silicate were made with asbestos fibers in the insulation. Asbestos is no longer used because it's been found to be hazardous to work with. So on older systems, you have to take extra precautions to avoid contact with the insulation. Since you're very likely to be working with calcium silicate, let's take a look at how it's installed. The insulation comes in half sections molded to fit around piping. The joints are staggered. Each joint on the right overlaps the two on the left. This makes the run stronger and prevents concentrated heat losses between joints. This insulation specialist is wearing all the necessary safety equipment. In case of slips, he's secured to the railing with a lifeline. The half sections are staggered, as shown before. Each section is wired to its opposite neighbor, locking the insulation together all the way down the length of the run. As the sections are mounted, they're loosely wired in place. Later, the wires will be twisted tight, and metal jackets will be banded over the insulation to strengthen the run and protect the insulation from damage. The next section is mounted on the opposite side. The end joints are butted together tightly so the insulation will prevent heat losses as effectively as possible. The first wire holds the section together while the worker adds a second wire. Wires are spaced at intervals of 1 foot, about 1/3 of a meter. With sections of this size, that means 3 wires per section. To tighten the wires, he takes up the slack with his finger, then gently taps the wire all the way around to sink it flush with the surface of the insulation. When it's flush, he finishes tightening the wire with a few good twists, trims the ends, and sinks them into the insulation with a couple of taps. The remaining wires are tightened the same way. When all wires are tightened flush with the insulation, the mechanic measures the piece for a jacket. In this case, the jacket must fit around a steam pipe hanger. He cuts holes for the hanger and for the nut on the bottom. When the jacket is trimmed to fit, it's mounted over the insulation. Each jacket overlaps the other by 3 inches, about 7.5 centimeters. One edge tucks under the neighboring jacket, and the other edge wraps around the outside. This helps lock the jackets together while providing for expansion space between the joints. This is important because as the pipe heats up, the metal expands, causing the pipe to become longer. This tends to spread the joints apart, leaving gaps between the sections of insulation. The overlapping jackets cover the gaps and help prevent heat losses between joints. Initially, the jacket is secured with wire ties. Wires are twisted on about 1 foot apart, just to hold the jacket tightly in place while it's banded. Even though they're only temporary, the wires are put on the jacket the same way they were installed on the insulation itself. At first, the wires are loosely twisted on, just to get their approximate position. Placement of the wires is not critical, but you have to think ahead. The bands go on next, so the mechanic makes sure to leave room for them by visualizing where they will go in advance. The bands will go between the wires, and then the wires will be snipped off. In this example, bands will be placed on either side of the pipe hanger to hold down the flaps, so wires are placed slightly further down the pipe, holding the flap tightly enough while still leaving room for the bands. When all the wires for a single jacket are in place, they're twisted tightly so the jacket fits snugly, but not so tight that the wire breaks. Remember, the metal jackets don't give like the insulation itself. The wires aren't embedded in the surface. The object is to hold the jacket in place so it forms a smooth, tight shell over the insulation with no buckling or loose spots. When the jacket is firmly in place, it can be banded. Bands are placed 1 foot apart, about 1/3 of a meter. Additional bands may be needed to hold down flaps from special cuts, like the cut for this hanger and the ends of the jacket. The first step is to position the bands. When they're all in place, they'll be tightened with a special tool. The mechanic wraps the band around the jacket and pushes the free end through the slot. He pulls on the free end to cinch the band tight and bends it up so it won't slip back through. At this point, it's not vital to get the bands extremely tight. The banding tool does that. What you want to do here is position the bands correctly and secure them loosely over the whole jacket. Just slip the band around the jacket, pull it tight, and bend the end up to hold it in place. Don't bend the soft metal back and forth unnecessarily. Metal fatigue will cause it to snap. This is a banding tool. Spreading the handles one way pulls the band tight. Pulling them in the opposite direction cuts off the free end of the band. The stub is bent over to keep it from pulling through, and it's held down by 2 tabs on the slot. Remove the piece of scrap from the banding tool and you're ready for another one. Slip the end of the band between the jaws and through the slot on the rotating piece. Spread the handles slightly as you bend the end down in line with the direction of pull. Spread the handles, bend the end up, and pull the handles the other way. Bend the end over so it won't pull through, and secure it by tapping the tabs down over it. This is only one kind of banding tool. Several different kinds are used, but they all do the same job. Pull the band tight and cut off the end. Whatever kind you use, be careful not to stretch the band so tight that it breaks. With practice, you'll learn just how tight the band can be without snapping. When all the bands on the jacket have been tightened, the mechanic removes the temporary wires. The bands should hold the jacket on so it's smooth and tight, no bulges or buckling. Jackets are mounted differently on vertical runs. To keep the jackets from sliding down the pipe, 3 S-clips are hung on the jacket below. The clips are made from scrap pieces of band, bent sharply at either end. The jackets overlap just as before. The clips support the weight of the jacket. At first, the jacket is secured with wires. Wrap the wires loosely. Then, tighten them so the jacket fits snugly over the insulation. The bands are positioned loosely. Tightened with the banding tool, and the wires are snipped off. Most calcium silicate installations are jacketed with metal, like the job you've just seen, but this isn't always the case. Sometimes the insulation is covered with canvas cloth called lagging. Sometimes straight runs are lagged, but more often lagging is used on elbows and other fittings where it's difficult to mount a metal jacket. Since these are the areas where maintenance is most frequent, you'll need to learn the skills for insulating these places. What we're about to see is a routine maintenance job on a lagged section of calcium silicate pipe insulation. The workers will be using 3 special materials: lagging cloth, insulating cement, also called mud, and finishing cement. Notice that the corners of this section are white. They're covered with lagging. A metal jacket covers the straight section in between. The first step is to remove the jacket. This jacket has been fastened with self-tapping screws instead of bands. They're taken out with a screw gun, and the jacket is removed. Next, the lagging is slit and peeled off the insulation. Then the wires are snipped off. The straight section of insulation is sawed off, since only part of it needs to be replaced. Then the outer layer can be removed. All scraps of used insulation are set aside to be properly disposed of. This insulation was installed in 2 layers to reduce heat losses to a minimum. The inside layer is removed the same way as the outside layer. The wires are snipped off one by one, and both halves are taken off and placed in plastic bags for disposal. The elbow was covered with insulating cement called mud when it was originally installed. The old cement must be chipped away before the wires can be removed. Each wire should be peeled off of the insulation to break up the mud and make the sections easier to remove. When the last wire is cut, the insulation can be taken off with no trouble. The pipe is inspected for cracks and corrosion before it's covered again. Before the insulation can be replaced, the new elbow insulation must be carefully trimmed to fit around the riser and the weld bead. Then, both halves are fitted over the elbow. If they've been trimmed correctly, the insulation fits close to the pipe all the way around, and both halves mate together with no gaps. The halves are wired together loosely. Then the wires are tightened and sunk flush with the surface. The straight gap is measured so new pieces of insulation can be cut to fit. The new sections are cut with a standard ripsaw. The insulation is mounted on the pipe, and the wires are tightened, just as before, flush with the surface of the insulation. The outer layer is put on so the seams do not match up with those of the inner layer. This helps prevent concentrated heat losses through the cracks between halves. The insulation is then wired on in the normal manner. Insulating cement is used to fill the remaining cracks. The mud is usually mixed up by hand on the spot in the exact quantities needed for the job. It's troweled into the cracks to seal off possible heat leaks and smoothed over the entire elbow. With a steady hand and a good eye, it's possible to form a hard, airtight shell that makes a nicely rounded, smooth surface for lagging. Before the elbow can be lagged, the lagging cloth must be cut to the correct size and shape. The worker measures the lagging cloth by laying it out against the elbow. Then the cloth is folded into a triangle and doubled over 3 times. The lagging is cut to the correct length with a sharp knife. When the cloth is unfolded, it forms a quarter circle, just the right shape to stretch over half of the elbow. The lagging is thoroughly wetted with finishing cement. It's brushed on almost like wallpaper paste. This mechanic uses a thin coating of cement on the box to hold the cloth in place while he wets it down. Next, the cloth is fitted to the pipe. It's smoothed down so no wrinkles mar the finish, and carefully trimmed to fit around irregularities. Finishing cement is then brushed over the outside of the lagging to stiffen the cloth and give the elbow a neat appearance. After lagging the other side of the elbow, all that remains is to replace the metal jacket on the straight section. The length of the section and the insulation circumference are measured with a tape. The jacket is cut with snips, secured to the insulation with self-tapping screws, and the job is complete. Well, we've spent a lot of time on calcium silicate insulation. That's because it's probably the most commonly used type of insulation in your plant. When you're working with calcium silicate, you'll need all the skills you've seen demonstrated here: installing sections and jackets on horizontal and vertical runs, and the lagging techniques that are usually used on corners and awkward fittings. Take a short break now to discuss the material with your instructor. Look through segment 2 of your text and work the exercises before going on to the next part. When we return, we'll be talking about how to keep things cool at the plant. So far in our discussion of insulation maintenance, we've seen men working with high-temperature calcium silicate insulation. What we're going to do now is look at three kinds of insulation that are used for low and medium temperature applications: fiberglass, cellular rubber, and plastic foam. Now, from our discussion of the functions of thermal insulation, you may remember that insulation can be used to keep systems hot or to keep systems cold. Cellular rubber and plastic foam are used to keep systems cold. Fiberglass can be used either way, as low-temperature insulation or high-temperature insulation, up to about 400 degrees Fahrenheit, 200 Celsius. Because of its two-way temperature range, fiberglass may also be used for some special applications. One of them is heat-traced piping systems. Heat tracing is a way to prevent the contents of a piping system from thickening or freezing in cold weather. A small steam line or an electric element heats the pipe along its length. The insulation keeps the heat from escaping. If it's an oil line, the oil will flow freely. If it's a water line, it won't freeze up, even if outside temperatures are very low. The first maintenance procedure we're going to see is the replacement of fiberglass insulation on a heat-traced water line. You'll notice that the insulator wears a filter mask, goggles, gloves, and long sleeves. That's because fiberglass irritates your skin, eyes, and lungs wherever it touches you. He's taken one additional precaution. He's made sure that the electrical heat tracing has been turned off and tagged out. As you can see, this insulation is badly in need of replacement. It's easily removed by cutting the tape with a sharp knife. But be careful. The flat plastic element is the electrical heat tracing. When you're working on runs that are heat traced, be careful not to damage the tracing with your tools. It could be a shocking experience. Now, even though it's tagged out, when it's turned on again, a damaged heating element can cause real problems. The new fiberglass insulation comes in preformed pipe sections with seams along the length where the insulation opens up. One side of the seam laps over to hold the insulation on the pipe. The lap seam is stapled all the way up. The staples should be spaced about 6 inches apart, approximately 15 centimeters. The end joints are sealed with tape to prevent heat losses through the cracks between sections. The ends of the tape are stapled to make extra sure it'll stay on. The seams are covered with cement to help seal out moisture that would tend to condense on the pipe in warmer weather. A good thick coating seals in the seam and plugs up the holes made by the staples. Working with fiberglass isn't difficult. It's light, easy to handle, and any special trimming can be done with a sharp knife. The example we've just seen demonstrated was the installation of pre-made fiberglass insulation for piping systems. But you're also likely to see this kind of insulation used in several different forms. It comes in blankets, stiff boards, and loose bats for different purposes. Whatever form it comes in, the same safety precautions apply: eye protection, a filter mask, gloves, and long sleeves. The important thing is to keep the fibers off your skin and out of your eyes and lungs. Fiberglass is one of the more versatile kinds of insulation. It's used both for low temperatures and high temperatures, up to 400 degrees Fahrenheit, 200 Celsius. Let's move on now and take a look at some kinds of insulation that are used especially for low temperatures: cellular rubber and plastic foam. Cellular rubber and plastic foam insulation come in tubular sections for insulating chilled water or refrigerant lines. They also come in blocks and sheets for special applications. The material is filled with thousands of tiny bubbles that act as dead airspace between the pipe and the outside air. Cellular rubber is made with closed cells. The bubbles don't interconnect. Plastic foam can be made either with closed cells or with open cells, where each cell is connected with others in the material. Both kinds of low-temperature insulation look pretty much the same and perform the same functions. They keep the pipe cold, and keep moisture away from the pipe. The outside of the insulation acts as a barrier to keep water vapor from entering. If the vapor barrier is punctured, water vapor can enter the insulation and condense on the cold piping. Condensed water dripping from cold pipelines can damage sensitive equipment below, or create a safety hazard by forming a puddle on the floor. Cellular rubber and plastic foam both provide their own vapor barrier, but they have to seal properly. Let's watch as a workman repairs the cellular rubber insulation on a chilled water line and see how it's done. First, the damaged section is cut away from the rest of the insulation with a sharp knife. Cutting the ends squarely will make it easier to fit the new piece when the insulation is replaced. Once the ends are cut, the piece is removed from the pipe. Next, a length of new insulation is laid out along the gap. The new section will have to be cut to exactly the same length. He marks the distance with a shallow knife cut. Then he lays the section down and cuts the new piece to the correct size. This type of insulation comes in tubular sleeves. To fit it over a pipe that's already installed, it has to be slit along its length. On new installations, the rubber sleeves are usually just slipped over the ends of the pipes before the pipes are put up. To seal all the joints tightly, a special adhesive is used on all surfaces with rubber-to-rubber contact. First, adhesive is spread on either side of the gap. Then, the ends of the new piece are prepared. The adhesive sets up on contact, holding the insulation together and providing an airtight seal against water vapor in the air. Both sides of the long seam are brushed with the adhesive so they'll stick together as soon as they touch. When all the seams are coated with adhesive, the insulation is mounted on the pipe. Squeezing the seams sticks the insulation together, so the worker has to get it right the first time, or the job may have to be done over. He starts at one end and works toward the middle, then starts again at the other end and works back. That way, he knows the ends will match up when he's done. The usefulness of the insulation largely depends on the quality of the vapor barrier. All the seams must be carefully sealed to keep water vapor out. Working with cellular rubber insulation is pretty easy if you remember that the important thing is to make seams and joints airtight. Plastic foam works the same way. It's installed like cellular rubber. One difference is that it's likely to be more rigid. Otherwise, they're very similar. In this segment, we've discussed two kinds of low-temperature insulation, plastic foam and cellular rubber. And we've seen one kind that can be used both for low and high-temperature applications, fiberglass. When we return, we'll be looking at a kind of insulation that can be used at any temperature, from the lowest to the highest. Meanwhile, take a short break. From our discussion on how thermal insulation works, you may recall that we talked about two basic kinds of materials that prevent the movement of heat: mass-type insulation and reflective insulation. What we're going to talk about now is reflective insulation. In the last two segments, we've looked at insulation maintenance techniques with several kinds of mass-type insulation: calcium silicate, fiberglass, cellular rubber, and plastic foam are all mass-type insulation. They contain dead air space to prevent heat losses from conduction and convection. Some of these kinds of mass-type insulation are used for high temperatures, and some can only be used for low temperatures. Calcium silicate is high-temperature insulation. It's good up to 1,000 degrees Fahrenheit or 540 Celsius. Fiberglass insulation can be used as high-temperature insulation up to around 400 degrees Fahrenheit, 200 degrees Celsius. Or, with the addition of a vapor barrier, fiberglass can be used as low-temperature insulation. Cellular rubber and plastic foam are both used exclusively for low temperatures. If they're used for high temperatures, the insulation will melt. Reflective insulation is different. It's good for all temperature ranges, for low temperatures and high temperatures, right up to the highest temperatures found in the plant. Reflective insulation works by bouncing radiant heat back to its source. Heat can't get through because it's reflected back from where it came. The insulation is made of shiny metal, often stainless steel, or sometimes aluminum. On piping systems, the insulation can be used in several different ways. Some kinds of reflective pipe insulation use many layers of thin foil to keep heat in. Each layer reflects some of the heat, so very little escapes to the outside. Other kinds of reflective insulation are used along with mass type. The mass type insulation is sandwiched between sheets of metal, providing a dead air space for additional insulation value. In a minute, we'll be looking at several different kinds of reflective insulation and talking about how these insulation systems are maintained. But first, let's talk about where and why reflective insulation is used. The first place you might find reflective insulation is on piping systems that operate at very high temperatures. When temperatures reach a certain point, it's just not practical to use mass-type insulation. It fails too quickly. You're also likely to find reflective insulation used in any plant area that has to be kept very clean. In this case, reflective insulation is used because it's clean. It doesn't release dust or fibers that can get into the air. Some chemical processing plants have these kinds of clean areas. Also, in certain areas of nuclear power plants, reflective insulation is required because it can be decontaminated easily. In these clean areas, your most common insulation maintenance task will be removing the insulation and replacing it during routine maintenance of the system. So, with that in mind, let's take a look at some of the reflective insulation materials you may be working with. Here's an example of many layers of metal foil being used to prevent heat losses. The space between the layers adds insulation value to the piece. Dead air helps keep the heat in. This piece uses mass-type insulation along with reflective foil and sheet metal. The mass-type insulation is sealed between layers of foil, so dusts and fibers can't escape into the clean area. Pieces for elbows, corners, and special fittings are usually fabricated to fit a particular system by the manufacturer. Each of these special pieces is designed specifically for one installation. There may be only one place where the piece will fit correctly. When the insulation system must be disassembled for maintenance, each piece should be carefully marked so it goes back in the right place. The pieces should be numbered in order, and each edge mark to show where it connects to the next section. The sections are held together with spring clips like this one. To remove a section, unclip the latch, and the piece opens up for removal. Each piece has a flange that slips over the end of the next piece in line. When the insulation goes back on, sections are latched around the pipe one at a time, and the flanges lap over for effective insulating. Be careful not to pinch your fingers when sliding the insulation together. Watch yourself on sharp corners, too. Many of the specially made pieces may be roughly finished. Jagged edges and rough corners make gloves a must when working with reflective insulation. You should always watch out for yourself. But try to avoid damaging the insulation, too. Since each piece will be used over and over again, removed and replaced many times, it's especially important to keep the insulation in good shape. Even though it's made of metal, it's easy to damage this kind of insulation. If the thin metal foil on this piece is torn or cut, the mass-type insulation inside will be exposed, and some may escape, making the entire piece unusable in a clean environment. Reflective insulation is very specialized equipment. Often each piece is made especially for one job. Aside from the necessary insulation value, it has two important characteristics. One, it's clean. No dusts or fibers can escape into the area. And two, it's easily removed and reinstalled for routine maintenance. When you work with reflective insulation, you'll be given detailed instructions on how to handle the job. The important thing is to prevent damaging yourself and the insulation. Wear gloves and handle the insulation carefully. It's expensive stuff, and if a piece is damaged, it may take a long time to get a replacement piece fabricated. By now, we've looked at all the most common kinds of insulation you're likely to be working with. We've seen how they work, where and why they're used, and we've discussed the maintenance techniques you'll need when working with each kind. In a few minutes, we'll be talking about some tips you can use to make working with insulation safer and easier. But until then, take a short break. By now, we've seen examples of maintenance techniques for working with several of the most common kinds of insulating materials: calcium silicate, fiberglass, cellular rubber, and reflective insulation. You've probably noticed that in every case, the workers involved were wearing some kind of special protective clothing. When they were working with fiberglass and calcium silicate insulation, their basic protective items were goggles, filter masks, gloves, and long sleeves. There are some important reasons for wearing this gear when you're insulating. Let's take a close look at fiberglass and calcium silicate insulation and see how they affect your safety. Fiberglass insulation is made of thousands of tiny glass fibers. The fibers are sharp and easily penetrate exposed skin. Glass fibers cause severe irritation wherever they touch the skin. Fibers in the eyes can cause permanent damage to vision. Breathing glass fibers can make your nose and throat itchy and sore, and possibly cause lung problems later. If you work with fiberglass, wear your goggles and mask, and keep your skin covered to prevent contact with the insulation. Calcium silicate insulation presents a different safety hazard. It makes sense to keep any kind of dust out of your eyes and lungs. But with some kinds of calcium silicate insulation, there's an even more important reason to protect yourself. In the past, many kinds of calcium silicate contained asbestos fibers for added insulation value. Since then, asbestos has been found to cause lung cancer and contribute to other respiratory diseases. It's no longer used in insulation, but if you're going to be repairing or ripping down older insulation systems, you may be in contact with asbestos. Wherever you might be working with asbestos, use all the precautions you can to keep it out of your lungs. Dispose of scraps and used insulation properly. They should be removed in sealed plastic bags. When you're done, vacuum the floor and your clothes to prevent spreading asbestos dust around. Asbestos is one of the best reasons for wearing the right protective equipment for the job. But any time you're exposed to dust or glass fiber from insulation, you need to protect your lungs and eyes. With reflective insulation, you don't need goggles and a filter mask, but you do need gloves. Reflective insulation is usually made of sheet metal with sharp corners and edges. Whenever you handle sheet metal, you should wear gloves to protect your hands from cuts. This is especially true with reflective insulation. Since it's often custom-made for the plant, the edges and corners are not always finished as perfectly as production line products. Exercising care when handling reflective insulation can keep you from getting a nasty cut. Working around hot pipes is another occupational hazard for insulators. Be alert to the signals of heat stress. Dizziness, cramps, or nausea are all signs that your body is overheating. Drinking small amounts of water frequently while you're working helps your body cool off. Gloves are a must when working close to hot pipes. You can get a bad burn just by accidentally brushing the pipe with your bare hand. Use good sense when working in hot areas. It takes a while for your body to adjust to the heat. If you feel yourself overheating, take a break to cool off. Ladders are another hazard that insulators have to deal with. A straight or extension ladder has to be braced by a second person or tied off at the top. And don't stretch your luck by standing on the top rung. The highest you should go on any ladder is 2 rungs below the top one. Wearing a lifeline can be a good idea, especially when you're high up in the plant. A short length of cable is easily hooked around a rail, but be careful when you're close to electrical equipment. The cable should be grounded, or a non-conductive rope should be used to reduce the shock hazard. Electrical heat tracing can shock you too. Before working on heat-traced runs, make sure the tracing has been turned off and tagged out. Some of these hazards are not unique to insulation work. You could run into them on many different kinds of jobs. There are some special hazards, though, that are directly related to insulation, and they affect not only the worker on the job, but the whole plant as well. We're going to talk about 2 special problems: stress corrosion cracking and oil-soaked insulation. Stress corrosion cracking can be a problem with certain kinds of stainless steel. When insulation containing chlorides is in contact with these steels, a chemical reaction between the insulation and the metal weakens the steel as it's corroded. This cracks the stainless steel, causing leaks and possibly causing the shutdown of vital systems in the plant. So when you're working on a stainless steel run, only use insulation that's certified to be chloride-free. And when the insulation is off, carefully inspect the pipe for cracks and leaks. When you find a leak, look for the source. Is it water dripping from a pipeline overhead? Or is it oil, possibly from within the insulation? Oil leaks can be a special problem because sometimes the oil catches fire and smolders under the insulation. Smoldering insulation may not be noticed immediately, but when someone cuts into the insulation to repair it and see what's causing a leak, the sudden rush of fresh air to the smoldering insulation can cause a sudden flare-up, and someone could be barbecued. Whenever you remove oil-soaked insulation on hot piping, have a helper with a fire extinguisher standing by in case of a flare-up. Start by removing sections as far away from the soaked area as possible and gradually work your way closer to the soaked spot. That way you'll have plenty of warning before the insulation bursts into flames. Remembering simple safety precautions and using the correct equipment are the best ways to avoid getting hurt on the job. Your safety equipment is especially important when you're working with hazardous substances like asbestos or irritating kinds of insulation like fiberglass. Goggles, a filter mask, gloves, and long sleeves are standard gear for insulation installers. Make good safety practices a habit, and you'll be well on your way to becoming an efficient and safe insulation worker.